Hello, thank you very much for joining my presentation. My name is Kamil Rzechowski and I'm Senior Machine Learning Engineer in ReasonFit Lab. Originally I'm from Poland and today I will talk about cashierless AI-powered shops. Alright, so imagine a situation that it is a holiday day and all regular grocery stores are closed, but you need to do the grocery. Or maybe it's right before the holiday weekend and all grocery stores are packed with people doing shopping for the long weekend, and even the self-checkout lines are long. Wouldn't it be nice to do the shopping whenever you want rather than tracking all holiday dates and sticking to opening hours? Wouldn't it be nice to have a way around the crowds and long waiting queues? Or imagine one more situation. Maybe you have to buy something you would rather not anyone see you leaving the store with. How cool it would be to have a full privacy when doing shopping. So this is kind of an idea behind cashier-free shops, a concept grocery store that allows you to walk in, grab what you need, or maybe something you don't, and walk right out without a checkout. Amazon calls this technology Just Walk Out. There are already over 25 Amazon Go stores in US and 17 in UK. Amazon is the first company to open cashierless stores. However, there are already other companies doing it as well. For example, German Aldi opened the first cashier-free store in UK. Same with Tesco and Sainsbury. Poland, my original country, has its own cashierless store chain called Żabka with double P. It already opened about 40 stores across Poland. So, firstly, I will show what the cashierless store looks like from the customer perspective. Later on, we will move to the technical details, which is something that we all are waiting for. But let's first start with the customer journey. So how it works. First of all, you need to have a smartphone. You download the app, register, add your credit card details, generate the QR code, and scan it in order to enter the shop. When you are inside, multiple ceiling-mounted cameras track your every move. Everything you grab is charged on you. If you change your mind, you just put the product back on the shelf. The item automatically comes out of your virtual card. When you are done, you simply walk out. Zero human interaction, you don't need to talk to anybody. On the side note, it's great for introverts. There are no human cashiers, no checkouts, no waiting queues. Your account is charged automatically when you exit the grocery store. If you would like to enter the shop with your child or with your friends, you can use the same QR code you used to enter the grocery store by yourself. But you need to keep in mind that everything they grab from shelves is charged on you. And another important notice is don't hand over products to other customers. So if you picked something from the shelf, if you hand it over to someone else, the product is still charged on you. So if you change your mind, just put it back and it will automatically come out of your card, but don't hand it over to other customers unless you want to give them a gift. We already saw the journey from the customer perspective. So let's right now deep dive into the technology behind cashierless stores, something that we gathered here for. There are several challenges in front of cashierless stores. First of all, the system has to accurately identify customers who enter the store, track customers through the store, and associate shoppers with items they retrieve from shelves. Everything without facial recognition, which is banned in many countries due to the privacy reasons. The system has to re-identify people based on their unique color, outfit features, height, and probable location. Moreover, the system has to be robust to visual occlusions resulting from multiple concurrent shoppers. Amazon mentions that it was one of the biggest challenges before launching of their first supermarket, as similarly looking customers used to be re-identified. The system has to be robust to concurrent items retrieval, as different products may look the same. It addresses both visual and weight similarities between items. Last but not least, the system has to be robust to fraud, especially to attempts by shoppers to confuse identification, tracking, or association. Finally, it has to work in real time, which means it has to be highly optimized and achieve high accuracy on the other hand. Everything without special marks, sensors, electronic identification, everything that could detract from the shopping experience. All of that is possible because of specialized hardware and of course AI. Cashierless shopping is achieved using a network system containing several sensors fused together. Most cashier-free stores are based on a significant amount of cameras mounted on the ceiling with an overlapping field of view. Those can be calibrated 2D cameras or more advanced 3D cameras. Moreover, the shelf load sensors are very helpful, and sometimes RFIDs can be used to double secure the more expensive items. The shelf weight sensor along with cameras are used in Amazon Go stores. Weight sensors can help identify items removal from the shelf, even if the item is completely occluded. Using such sensors requires, however, the shop to redesign and purchase more expensive shelves. The correct sensor fusion is crucial for building a robust and efficient system. And building a robust cashier-free system requires connecting following technologies from the AI world. So firstly, customer and product detection, post tracking, re-identification of shoppers without facial recognitions, as I mentioned before, human action recognition, and sensor fusion of cameras, weight sensors, and RFIDs. As we can see, there is a lot from AI field, and therefore cashierless stores are such a hot topic in AI. Right now, maybe slightly less hot topic because of LLMs, but still. Okay, so we saw the customer journey at the beginning of the presentation. Let's make right now the same journey, but from the technology perspective. Everything starts when we scan our QR code in order to enter the supermarket. Multiple camera mounted on the ceiling, mounted cameras on the ceiling, start to track our move. But how is it done? An example implementation of the multi-object tracking algorithm achieving real-time performance is StrongSort. StrongSort is, on the side note, is improved version of DeepSort. It identifies customers in a single camera view using a YOLO object detector. Further, it uses a cascade algorithm to assign newly detected objects to their ancestors from previous frames. The first stage uses the Kalman filter to predict person location in the following frame, and the re-identification feature vector obtained from the feature extractor neural network. Then, the association cost matrix is created based on Kalman location prediction and re-identification features, and the linear assignment problem is solved using Hungarian algorithm. The second stage takes unconfirmed and unmatched tracks and runs intersection over union on them in order to further improve the assignment. Objects that have a high overlap area are assigned as the same objects. And this is the identification in a single frame, in the single camera. The next stage is association of the same objects on the multiple camera level. So camera talking to each other. It is performed in a very similar way. If we have a 3D object location, we can use object location for association purpose. Otherwise, if we don't have the 3D location, we can rely on re-identification feature vector for the assignment problem. Luckily, the store usually have multiple overlapping and calibrated mountain ceiling cameras. The store topology is known a priori, and by utilizing those information, we can do even better. We can re-identify person not only based on appearance features, but also using the 3D shopper location. Okay, so let's start with saying that we are more interested in tracking the skeleton than bounding box. It will be particularly useful for product retrieval detection. The human skeleton can be accurately predicted, for example, with OpenPose. OpenPose is very suitable for this task as it achieves high frame rate, which is something we deserve in shops with many multiple ceiling mounted cameras. We can of course mount on the ceiling. We can use 3D cameras, but those are more expensive and also more expensive in processing. However, in multi-view geometry, constructing the location of a point in 3D space requires knowing the 2D location of the point in at least 2 views. So we don't really need 3D cameras. We can use 2D cameras if we have multiple, but those cameras need to have overlapping field of views. And to achieve that, we need to cover each store area by at least 2 cameras. The more the better. The occurrence might happen from 1 camera view, so if we have 3 cameras or 4 with overlapping field of view, it's even better. So we can estimate joint location in 2D using OpenPose in each camera independently, and then assign the same person among cameras. Knowing those assignments, we can estimate the 3D human skeleton. Here, the assignment process can be computed in 1 stage. Knowing the 3D skeleton location, we compare the newly detected skeleton with the one from the previous frames, both in 2D and 3D. Here, I assume that we have a 3D skeleton location. Okay, of course, in the first frame, when the customer enters the store, we don't have, but we can build it or assume it or make it a rough 3D skeleton, and then knowing the 3D skeleton from the previous frames, then we use it in the next frames, and it is iterative algorithm. As presented here in the image, we compare joint locations between frames in 2D. So yeah, we can compare those of, for example, for this person is the green one is it's the same time from different ceiling mounted cameras, and we can compare the joint locations between those frames in 2D. Further, using the camera projection matrix, we can find a line that maps all points lying on this line to the joint position in the image. Then we can calculate the point to line distance in 3D, combine those 2 pieces of information, allows us to build a robust assignment cost matrix and solve the assignment problem in the Hungarian algorithm. The algorithm is run independently on each camera frame, and the same person is in each view is re-identified. Knowing the same person from different camera views, we allows for reconstructing a new 3D skeleton. Of course, everything can be simplified using a 3D camera, but as I said previously, 3D skeleton estimation can be done using only a single camera, and it's more cost efficient. And the proposed algorithm, is also very fast. Okay, so we are done with multiple camera multi-object tracking challenge. Let's now take a closer look at the open pose algorithm. Open pose is a popular and accurate algorithm for multiple body pose estimation in a single camera view. The algorithm takes as an input the RGB image and produces a set of 2D confidence maps of body parts locations, as one map for each body joint, and a set of 2D vector fields, which encodes a degree of association between body parts. Finally, the 2D confidence maps and 2D vector fields are parsed together to output the 2D key point for all people in the image. And this is the algorithm works really well. However, there might happen the limb association confusion, especially if multiple people's arms are close to each other. The correct limb association is crucial for identification who took which product. We don't want to charge person A for products taken by person B and vice versa. The misalignment can be improved. The open pose treats each limb independently, resulting in a case where the elbow key point from one person can be associated with the wrist key point from another person. To avoid this failure, one person's forearm or upper arm should be treated as a pair. For identification forearms as belonging to the same person, the Euclidean distance between one forearm histogram and the second forearm histogram can be measured. Further, the open pose association algorithm can be modified in a way to favor associations with small Euclidean histogram distance and penalize connections with large Euclidean histogram distance. And by doing that, we can increase the algorithm confidence in limb association. For appearance matching, the most intuitive solution is feature matching, where features are obtained by the CNN feature extractor or maybe attention feature computer vision transformer network. Most CNN-based feature extractors like ResNet were originally designed for object category level recognition task that is fundamentally different from the instance level recognition task in re-identification. In category level recognition task, we try to distinguish between, for example, car and a human, while in the instance level recognition task, we try to distinguish one person from the other. It is not a big surprise that features required by the re-identification task are fundamentally different from category level identification tasks. For the later re-identification task, omni-scale features are more important. But what are those omni-scale features? Features of both homogeneous and heterogeneous scales combined together. So let's make an example. The top image presents two different persons. Looking only at the global scale features, example, young man, a white t-shirt plus gray shorts, would not allow to distinguish the true match. Middle, an impostor, and an impostor right. Now the local scale features come into play. The true region gives away the fact that the person on the right is an impostor. Trainers versus shoes. Trainers versus sandals. So to match people and distinguish them from impostor, features corresponding small local regions, for example shoes, glasses, and global whole body regions are equally important. The lightweighted neural network for instance level recognition task was proposed by authors of OSNet, Omni-scale features learning. The network has about 2 million trainable parameters, and it does pretty good job in identification tasks. Sorry, here is person A and here is person B. I also identify those persons. Okay, so we already covered the whole tracking pipeline and shoppers' identification. When shoppers is being constantly tracked and their hand movements accurately detected, the next step is to recognize hand actions, especially to identify items that the shopper picks up from shelves. Vision-based hand tracking alone might be inefficient due to multiple shoppers concurrently accessing products under variable light conditions. So apart from vision-based systems, very often also the shelf-mounted weight sensors are used, and proximity event detection. What is the proximity event detection? When the shopper's hand approaches the shelf to grab or return the product, the grab or return action is probable to happen. The proximity event and the correct shelf is chosen based on the Euclidean distance of the hand to the shelf. And from previous slides, we know the hand 3D location, we know the shelf's location because we know the 3D shop topology, so we can easily compute the Euclidean distance in 3D. So when the pickup action is probable to happen, the correct shelf is chosen and the weight sensor in this shelf is monitored. If the item is removed from the shelf, there is a peak in the weight sensor reading. We can see those drops. And to solve the problem of distinguishing between two items and similar weights, visual features are used. The fastest solution is to compare the histogram of picked item with the histogram of the items in the database. And we can use, for example, KNN classifier for this purpose. However, sometimes histogram comparison might not be enough. Then the CNN feature extractor, for example, Omni-scale net mentioned on previous slides, the same that was used for identification features can be used. Everything can be packed into LSTM-based architecture that outputs the probability that item was picked or not. One potential problem here might be simultaneous item retrieval by multiple customers. However, having a weight sensor running with, for example, 30 Hz sampling rates ensures that the peak in the weight sensor reading should be distinguishable between each other. The last step in product identification is the product identification. One approach is to use object detector and histogram comparison as described in the previous slide with items retrieval detection. Moreover, the background and hand can be subtracted from the image in order to narrow the histogram only to the item histogram. Another approach is to use the standard object detector, like for example, YOLO object detector is a good choice as it is fast and accurate. However, training a robust object detector requires a significant amount of training data. Self-supervised techniques can be used to extract information from unlabeled data. However, A better approach might be to generate a synthetic dataset and train the YOLO on this dataset. Having a 3D CAD model for each item in the supermarket can help create a huge label dataset that is very suitable for training object detector. Object detector might also be helpful in identification of misplaced products. Misplaced products should be reported to the shop service and fixed, as it may introduce errors in the shop system, cashierless shop system. However, the customer, we don't want, as the shop owner, we don't want to charge customers for misplacing a product or charge wrongly for tracking a misplaced product. Therefore, the product location is important in deciding which product was retrieved, but it's not something that we must take for granted that the given product is located in a given place. And the product identity should be checked every time a pickup or return gesture is recognized. In cashier fee shops, products should be localized in a way that similar products are not next to each other. So if we plan a cashierless stores, we should separate similarly looking, both in similarly looking and similar in terms of weight products. We should separate them in different shop areas. Moreover, if we design a cashierless stores, a computer readable pattern can be added to a similar product in order to increase the object detector confidence. Okay, so we are done with our technical journey. It was quite a technical deep dive, so I hope you followed up and got something from that. I will be also later on available for questions about the technical details, so if you missed something or want a clarification, I will be happy to answer. And right now we are done with our technical journey. We took what we want from shells, packed right into the backpack and go out without checkout. Designing and implementing a cashier fee store is a challenging task. It requires usage of all main state-of-art technologies and in computer vision and machine learning. Moreover, it is challenging task from performance optimization perspective and sensor fusion. Cashierless stores require a significant amount of processing power. The other main challenges that cashier-free stores have to overcome it was partially mentioned in the presentation. The common problem in customer or link confusion. The customer's confusion can be solved by installing more cameras, but on the other hand, it adds system complexity. The maximum number of customers that can be successfully tracked or identified is a limiting factor. So in order to overcome this, in order to reduce the chance of customer confusion, the shop may decide to limit the number of customers that can enter the shop. Limb confusion can be overcome by considering limbs of one person as a pair rather than a separate limb, as I mentioned on the OpenCV slide. OpenPOS slide. Finally, there is a set of products that look very similar, and for those products, for example, a prepared salad with salmon salad with the For example, a prepared salad with salmon and salad with chicken. Those, from the box perspective, look exactly the same. In order to distinguish more those products one from another, the computer readable patterns can be added to the salad box, and that's something that Amazon Go did in their Amazon Go shop. So, what are the benefits of cashierless stores? There are actually many. We can monitor shoppers' behavior, collect those data, do some statistics, propose better shops for customers, prepare, get restocking more often with products that customers like. We have live inventory management, so we know which products are running out of stock and which should be restocked. That's great for shop management. We have operational costs going down. Of course, this is the investment cost is quite huge for the system like that, but in the long-term perspective, we can save operational costs. We also have more in-store selling space because we don't need a place for checkout. The shopping is quicker. That's something that definitely customers would love, that they don't need to stay in long waiting queues. We have increase in transaction volume. It's very easy to just grab the product from the shelf and put it into the backpack. Of course, it's the benefit for the shop. Maybe it's not such a benefit for the customer because they need to pay more. But here I'm talking generally about different benefits. And we have theft reduction. So most thefts happen inside the shop where users pack directly their products in the bag. In cashierless stores, it's something that the shop is designed for. So this using this approach, the theft reduction is reduced. Someone may ask, are humans still needed? Yes, they are. They are needed for risking shelves, checking IDs in the alcohol section, preparing food, and for security reasons. But all those people are already needed. So, yes, there are some people still needed in cashierless stores, but definitely there is less people needed in cashierless stores than regular stores. Thank you very much. I hope you enjoyed the presentation. I will be available for any questions, so I would be very happy to answer and clarify any questions that you have in mind. Thank you very much.